We're going to take notes on the Canvas lesson. So I made a slideshow for you guys. If you already took notes on this, then you can feel free to just have your notes out and you can actually just add to them, maybe emphasize certain things, underline, highlight, etc. To pay attention to what's going on, because I'm going to just kind of emphasize the most important stuff here. So the interesting thing about enthalpy and entropy is that it is going to result in us looking at an equation, but it's not really math. It's more like critical thinking and analyzing of the equation. So keep that in mind. We're not going to necessarily solve the equation, at least not yet. You would eventually if you stay doing higher level chem work. So our objectives today are going to be to define enthalpy and entropy and predict the spontaneity of a reaction. So it's important for chemists to be able to predict what's going to happen in a reaction, because really that shows that we understand what's happening in that reaction. Hi, Michael, you're in the live class right now. So what we're going to do is start with this warm-up question. True or false, all things tend toward chaos? I know this is kind of like a philosophical question as well. But what do you guys think? True or false, all things tend toward chaos? True. Yeah, right? So this is actually one of those things where if you're just an inherently messy person, right, like I am, as you can see, like my setup right now, I have like 20 things out. Not organized, right? Could I be organized? Sure, right, if I wanted to be. But this is actually the natural state of the universe, and I'm just contributing to it. That's how I look at it, right? So really, orderly stuff is not the way that the universe wants to be, right? So even if you spend a lot of time organizing and putting things in a place, over time, it will just naturally evolve into chaos unless you're constantly organizing, which is why you have to constantly organize, right? Which is, for some people, fun, and for some people like me, misery. So all things do tend toward chaos. We call that entropy. So we're going to do some definitions here. You should definitely write these things down. We have enthalpy, entropy, and then spontaneous. We might know what spontaneous means, but we're going to talk about specifically what it means in a reaction. So enthalpy is the total heat content of a system. So when we're thinking about enthalpy, we're really thinking about, is the system losing heat? Is it gaining heat? Of course, heat doesn't ever go away, right? But it might leave the system. So it might go into space, for example, right? Or leave the reaction, then it's no longer in the system. So when we think about a system, we want to think about a reaction. At least in terms of chemistry, that's what we're going to be looking at. Entropy, we abbreviate by a triangle S. That triangle actually means change in. So anytime you see a triangle like that in math or science, it usually is in reference to a change. Entropy is the degree of disorder in a system or randomness. So more entropy would mean that it's more disordered, it's more random. Less entropy would mean that it's more organized and less random. And we'll look at quite a few examples of when entropy increases, specifically within a reaction. And again, that system in this case is meaning reaction. And spontaneous means the ability of a reaction to happen without any outside heat, cooling, or stirring. Right, so that means that if you take, for example, baking soda and vinegar, that is a spontaneous reaction. If you put baking soda and vinegar together, they react, right? You don't have to do anything except put them together. You don't have to stir, you don't have to heat them, you don't have to cool them. right? So that's a reaction that's spontaneous. That one also happens to be pretty instant, right? It immediately starts happening and it goes pretty quickly. Spontaneous doesn't have to be instant. Other reactions happen all the time, right? Especially like decomposition reactions will happen really, really slowly over time. So hydrogen peroxide, H2O2, the stuff that you pour on cuts, that over time will break down into water and oxygen. It will break down not necessarily super quickly, right? It takes years and years, but it will. Okay, so that's an example of a reaction that is spontaneous, but it's not instant, right? It's taking years. And that's often why a lot of things have expiration dates in terms of medicines, hydrogen peroxide, et cetera, is because that means that that reaction of decomposition is going to slowly happen over time. And, you know, if you're pouring water on your cut, it's not necessarily the same thing as pouring hydrogen peroxide, right? So you want to use the hydrogen peroxide. So after a few years, you're going to have to replace it. Okay, so here's some pictures of sort of what that looks like. So entropy is going to be best represented by this picture here on the right, with an insane amount of randomness, disorder, right? There's pieces of matter all over the place. It looks random, it looks chaotic. On the left, right, we have this highly ordered setup where these pieces are placed together in a certain way. Naturally, over time, if we did nothing, this highly ordered ball would break into this crazy, chaotic, entropic mass here. We can do things to help speed that up, right? Which we will learn about in reactions. Enthalpy, on the other hand, is more about the heat. Is heat getting absorbed in a reaction? Is it being released, right? How is that change in heat occurring? Is it releasing more heat than it's absorbing? Is it absorbing more heat than it's releasing, right? That's going to actually sort of help us understand the reaction a little better. In an open system, which is usually what a reaction is, the pressure in the system remains constant, right? So whatever is being absorbed is being released to some extent. But essentially, it's basically looking at that change in heat. Okay. So other things to note, right? We have an example here that we'll look at, and then we're going to talk about sort of how does this apply specifically to a reaction. So reactions, right? Most spontaneous reactions are exothermic. So what does it mean for something to be exothermic?
Releasing energy.
Releasing energy, right? Exo, think about exiting, releasing. Exothermic reactions produce heat. Most spontaneous reactions or reactions that just occur on their own are exothermic, meaning they release heat. That would tell us, right, that that's a negative enthalpy change. We're losing heat in the reaction because it's leaving the reaction. So enthalpy can help us predict reactions in that kind of a way. However, there are some endothermic reactions that are also spontaneous, right? Which is when chemists went, oh man, we can't make clear, perfect rules about this. That's when we actually started to think, oh, other things are involved here, not just the heat and the basically sum of heat. We also have to look at entropy, right? And we also have to look at temperature. So phase changes are an example of entropy, because when something is a gas, that has the most entropy, that's the most chaotic. Gases can move around a lot, right? They're usually completely random and chaotic versus a solid, more orderly, molecules are packed together, right, making that solid shape. So temperature can play a huge role in that, right? Phase change happens because of temperature. So if you raise the temperature of a reaction, you most likely will increase the entropy, because you will hopefully raise something from a solid to a liquid, from a liquid to a gas, and increase that entropy. Okay, here is also an example of, I believe, someone else's slide here that I took from Google Images because I thought it was a really good representation. So let's apply this specifically to a reaction. We have a reaction here, right? The first thing that you want to do when you're thinking about entropy is you really want to look at the subscripts here of what state of matter is this in. So we have a gas, and a gas. Okay, so it's all gases. So really, entropy is not going to increase in terms of the phases. Then we want to think about other situations here. So the question that they're trying to answer here is, do you think this reaction will spontaneously occur at room temperature? Okay, so we're at room temperature. There's this picture here that's showing us kind of what happens when we go from a solid to a liquid to a gas, right, where we start off really orderly and then eventually get this random pattern. We want to think about, in this case, the number of molecules. We start off with 2 separate molecules, and we end up with just 1 molecule. So because of that, it's probably not spontaneous, because in that case, we're going from more chaos to less chaos. Now, is entropy enough alone to predict whether this would occur spontaneously? The answer is no. But when we look specifically at the entropy of a reaction, we want to think about things like that. Are the molecules changing states? Are we creating more molecules, less molecules? Is temperature involved, right? What's kind of going on? Is chaos happening, or is it being reduced? So some more examples of that. When does entropy go up? So it will go up when or if we go from a solid to a liquid to a gas, right? When we mix or dissolve something. So that's also a place where you would see that subscript AQ for aqueous, right? That is gonna, things dissolved in water have a pretty high entropy because they're dissolved. They're just floating around randomly. It's almost like being a gas. We're also going to see an increase in entropy when the number of the product moles is higher than the moles of the reactant. So if we have 1 mole of a reactant and 1 mole of another reactant, and our product has 15 moles, our product is going to have a lot more entropy because there's more moles, there's more stuff to produce chaos. So you can think about that too, right? If you only have 3 things, it's pretty easy for them to be organized. If you have 300 things, it's harder to organize, right? So the more molecules or the more moles of something you have, the more entropy. If we have an increase in temperature, so temperature is increased, entropy increases. Why? Things start moving faster. A higher mass causes more entropy. A weaker bond can cause more entropy. Why? Because then that molecule can be broken and rearranged easily. An increased complexity has more entropy. So if we're going from a simple molecule to a more complex molecule, that could be an increase in entropy. Now, this is where it gets hard because there's so many ways that this can be changed. So you might be saying in your mind, okay, I understand entropy is chaos, enthalpy is temperature, but how can we really use those to predict a reaction? So first, let's make sure we understand increase in entropy. We have 4 situations here. First one, dissolving salt in water. What do you guys think? Increase in entropy or no? So you could just type yes or no in the chat. Thank you, Abby. Yes. You agree with that, Janie Mae? Dissolving salt in water would increase the entropy, right? Why? Because now we had two things. Now we have salt floating around in water, moving and interacting randomly. Freezing water into ice. See a lot of no's. Why are you guys saying no?
The temperature's going down.
The temperature's going down, that's true, but we're going to a solid. So you guys are right. It's no. Just want to make sure. Right? So ice, first of all, is more organized. The molecules are stuck in a position because they're a solid, right? And you're also right, Janie Mae said the temperature is going down, right? So the entropy would be decreasing as we go to ice. Good. Okay, now we're going to look at a reaction. The reaction of carbon dioxide gas with a solid calcium oxide to produce solid calcium carbonate. So we're starting off with a gas and a solid. We're creating one product here that is a solid. What do you guys think? Are we increasing entropy in that reaction or decreasing? And give a reason why. Decrease because there's less moles in the product. That's one reason, right? We used to have 1 mole of each reactant, only 1 mole of product. Moles went down. That's a good reason to think decrease. Think about solid, liquid, and gas. We had a gas, now we have no gas, right? That would also be a decrease in entropy because our final product is only a solid. So those are both two good reasons there. Okay, what about this last example here? The decomposition of solid potassium chlorate to produce solid potassium chloride and oxygen gas. So in this case, we're starting off with 2 moles of a reactant and we're ending up with 5 moles of product. So what do you guys think? Are we increasing entropy or decreasing? Abby says, yes, it's increasing. There's more moles in the product. That's one reason. We also create a gas. That's another reason, right? That gas is now free to move around and create more chaos. So that would also be an increase in entropy. Okay, good. So we're getting entropy hopefully pretty well here. It's making sense, right? A lot of this is logic. Ask yourself, is more chaos happening? What does that mean in terms of chemistry? Are there more moles? Is there a heavier mass? Is there a gas being formed? And you'll start to see there's a lot of patterns for this. So then what we want to talk about next is kind of how we can sum all of this information into one idea. So we call this free energy, which is the amount of energy change in a system, and it can be summed up by an equation. So again, that triangle means change. So the change in energy, which we abbreviate as a G, named after Gibbs, the man who I'm pretty sure created this equation, right? So the change in energy is equal to the enthalpy change measured in kilojoules per mole, right? Mole to the -1 just means that mole's on the bottom of the denominator. So we would actually see that written like this. If I can even, I'm not very good at writing with this thing, but kilojoules per mole. There we go. Right, so a mole to the -1 just means that it's on the bottom of that fraction. The energy itself is also measured in kilojoules per mole. Temperature is measured in Kelvin, right? Remember Kelvin, that weird temperature that we talked about for 4 seconds once, and now it's coming back. So you would have to convert your temperature to Kelvin if we were mathematically solving this. And then our entropy change, right, is measured as the change in S. It's measured in joules per Kelvin times mole. So that one looks like joules per Kelvin, oops, it's not a very good K right there, times mole. Right, so anytime you see those negative ones like that, that just means that that's on the bottom of the fraction. They're writing it like that because in this case, they didn't write these units in terms of fractions. Now, why do you guys think that I'm making you write out what the units are? When have we ever cared about units? Units are what can define the answer. That's a great response by Abby. Why else? Think about a situation where maybe we cross out units.
Stoichiometry?
Yeah, stoichiometry, right? If we were going to actually mathematically solve this equation, we would want to make sure that our units are canceling correctly, that our Gibbs free energy change actually ends up being the right units. Right? So anytime we have an equation, we're always going to define the units because they're important. Okay, so where'd my eraser go? There it is. Okay. Oh, I forgot I have to erase each line on this. Okay. So now that we've talked about the equation, all we're going to do to solve these questions, at least to start, is we're actually going to think about the equation as a whole and what's changing and whether it would be spontaneous. So here's a really, really helpful chart. In fact, I'm going to be silent for about a minute here because I want you to actually write down these things. Okay, so let's start with our delta G, or our change in free energy. When will a reaction be spontaneous? When G is positive or when it's negative? When it's negative, right? So when the free energy change is negative, so a negative delta G, delta, by the way, is how you say that triangle, that means that the reaction will be spontaneous. A positive delta G means that no, the reaction will not be spontaneous. So in two cases, it's really easy to tell. If we have a negative enthalpy change because a reaction's exothermic, and we have a positive entropy change, we have an increase in entropy, so it's getting super chaotic and we're releasing heat, it's an exothermic reaction, then our reaction will be spontaneous at any temperature. If those are reversed, so we're decreasing entropy and we're an endothermic reaction, then no, that reaction cannot be spontaneous at any temperature. Then we have two sort of, it depends on this kind of situations. If we have an exothermic reaction with a decrease in entropy, then at low temperatures, the reaction will be spontaneous, right? If the temperature times the entropy is less than the enthalpy. And if we have an endothermic reaction with an increase in entropy, right, then only at high temperatures will we see a spontaneous reaction. So you kind of have to think about plugging numbers into the equation without plugging numbers into the equation, right? It's like what if kind of things. So this chart's super, super helpful because it gives you an idea. So you can ask yourself, okay, is my reaction exothermic? Cool. Am I increasing entropy? Yes. Okay, it's a spontaneous reaction. Am I decreasing entropy? Then I need to look at the temperature. So let's look at an example. The melting of ice has an enthalpy value of plus 333 kilojoules per kilogram. What is true about the spontaneity of this process? Well, first of all, let's write out the equation or look at the equation. We have our delta G is going to be equal to what? Oops, I believe it's delta H. Am I right here? Did anyone write the equation down? Minus temperature times delta S. Yes. Okay, sweet. I'm right. So again, what do these things mean? Free energy, enthalpy, temperature, entropy. Okay, so they're telling us that we have a positive value for delta H. What does that mean? If delta H is positive, does that mean we are endothermic or exothermic?
Endothermic.
It means we're endothermic. So this is an endothermic situation. A positive delta H will always mean endothermic. Okay, so thinking about that, let's think about the chart then. We have an endothermic reaction. We want to know when will this reaction occur spontaneously. So if we look back at the chart, we see that for an endothermic to be spontaneous, it's only going to happen at high temperatures, right? Because we have a positive delta H. That means we're definitely going to have a positive delta S as well, and it needs to be a high temperature. So if we look at our choices here, we would select spontaneous at high temperatures. I like that the first two choices are the same, which I didn't even realize. So our correct choice here would actually be C. Oops, can't see where my mouse is. C is correct, right? Because at a high temperature, this will be spontaneous. We will then get a negative delta G. Okay, so that's kind of how I would approach these questions. Write down what you know, determine what that means, look at the chart. So let's do a couple more examples here. You guys are going to try these next two on your own. Okay. So here are two further examples. The combustion of ethane gas has a negative enthalpy change, which means that it's exothermic, and a positive entropy change. So you're going to decide what that means. Negative enthalpy, so negative delta H, and positive entropy. So when you think you have figured that one out, please let me know with an A, B, C, or D. We're actually going to change choice B to low temperatures, because I believe that's what I meant to put there instead of all. So all temperatures, low temperatures, high temperatures, or no. Abby's guessing A. A is correct, right? Again, we want to confirm, we go back to the chart. Exothermic, a negative enthalpy change, positive entropy change. Spontaneous, yes, at any temperature. Okay. What about number 2? The process of freezing methane, so CH4 as a liquid into a solid, has a negative enthalpy change. And they give us that number. Now we want to think, what else do we need to know? Well, we need to know entropy. So we have a negative delta H. What do you guys think here? Are we increasing entropy or decreasing?
Decreasing.
We're decreasing entropy because we're going from a liquid to a solid. So that means we have a negative delta H, which is an exothermic reaction, and we have a negative entropy. So are we going to be spontaneous at all temperatures? No. When or what do we need, right? Well, we have a negative delta H and a positive, or excuse me, negative delta S. Only at low temperatures will this be spontaneous. So that's going to be choice B because I'm pretending that says low, right? So choice B would be correct here. Low temperatures would cause this. So here's an example where they give you enthalpy, but you have to think, is entropy increasing or decreasing, and then determine what that means. Okay, so that's the end of the virtual session, right? There are more practice questions in the Canvas course if you would like to do more practice. And I'm going to do this for a lot of these sessions. You're going to get bonus points for being live in the session. The code word for today is going to be that. So make sure you write the code word down. You can use it for bonus points on this quiz on free energy. You could use it on another quiz if you do really well on this quiz, right? However you guys want to use it. We are going to have a period of time where we're not going to have virtual sessions for a few weeks because of testing. So during that time, you know, it might be nice to have some bonus points too if you end up not doing well on something and you want to add them. Otherwise, that's our enthalpy, entropy, and free energy lesson. Thank you for a higher amount of participation today than the last session we had. And I will see you guys next week at 10.